Let's see how, thanks to EdiLus software, it is possible to proceed with the evaluation of existing buildings in reinforced concrete and how to define a design stage. A design stage in which we can intervene in the structure to achieve a structural improvement or seismic adaptation. When we open a new document, we must specify the type of building. In this case, we choose reinforced concrete and also the type of construction, which would be an existing building. Once the existing option is selected, the program tells us if the file we are about to model represents the surveyed situation, current situation, or the design stage model. As a general rule, we start with the current situation model. We access the working environment of the software, where we will proceed with the geometric definition of the model, but also loads, materials, and reinforcements. Let's start focusing on the peculiarities of existing buildings. In general, for existing buildings, one of the initial and crucial aspects is to define the level of knowledge of the asset. From the navigator tree, we access the calculation preferences for existing buildings, and here we can manually impose the level of knowledge, or we can choose to rely on the software by enabling the wizard option. Once selected, we return to the 3D environment. But now we can take advantage of the knowledge level view. Here we need to specify what is the available documentation. For example, we should specify if the geometry of the structure is known, because we have the original drawings of the structure and it's supported by the result of some tests performed. As for the knowledge of the construction details, we must specify to the software if we have the original drawings, or only partially or do not have them. For the knowledge of the materials, we must specify to the program if we have test certificates. Once we have included in the program what information and documentation we have available, we must also specify to the program what is the state of knowledge. We must specify to the program the points where we have carried out the tests. Also, the characteristics of the test must be specified, can be destructive tests, non-destructive tests, or even tests to know the detail of the reinforcement, such as the quantity and the arrangement of the rebar. At this point, the program based on all this information quantifies the level of knowledge of the structure. In this case, we see that the program is not able to specify a level of knowledge since the number of tests we have carried out is insufficient, so we must add new tests carried out. Let's use this survey tests tool. First of all, we need to characterize the type of test. Tests can be destructive, cylindrical, for which we need to specify the compressive strength. But in the same point we can carry out another non-destructive test with an impact hammer. In this case, we must specify the surface area of incidence of the test that will be a rebound index. In the same way, we can also carry out an ultrasonic test and in this case specify the speed. But, at some point, we maybe want to determining the amount and arrangement of steel of the reinforcement. So by activating this flag for the reinforcement detail, we tell the program that the detail of the reinforcement is known. In the same way, we can get a sample of steel to undergo a tensile test to measure the elastic limit tension, breakage, and elongation at breakage point. Once the tests have been added to the characteristics, we must specify the point where it was performed. In this case, the data of a single test doesn't allow the program to determine the level of knowledge of the materials. Therefore we must add some more tests. Now the software has a sufficient level of knowledge for the materials, but not in terms of knowledge of the construction details. So it will be necessary to specify further tests to add details of the reinforcements, quantity, and the arrangement of the bars and so on. When the software recognizes that an adequate number of structure data has been added, then suggests what level of knowledge of the structure has been acquired. Now that the level of knowledge has been defined, another important aspect for the evaluation of the existing building is the determination of the mechanical strength of the materials obtained in the invasive and non-invasive tests. Also, in this case, the structural engineer has all the freedom to access the archive of the materials, identify the folder of the reinforced concrete and add a new material. From this window it is possible to specify what is the average cubic resistance that we have obtained and that will influence the calculation. Alternatively, we can get support once again by the software. When we have defined the specific tests, through the materials assistant, we can ask the software to determine the average compressive strength of the concrete and the average tensile strength of the steel, directly from the values obtained in the tests. By selecting a certain number of tests, through the Materials Assistant object, we can tell the software, as we have carried out destructive or invasive tests and non-invasive or destructive tests, we will determine the value of the average cubic resistance of the concrete, and this material will be added to our archive. Once this material has been added to the archive, it must be assigned to the structural elements, i.e. the columns, beams, walls, etc. Another fundamental aspect of the evaluation of an existing reinforced concrete building is the definition of the reinforcements, since in the case will be the software to inserting the reinforcements in all the structural elements. When we have to evaluate an existing building, it will be the structural engineer who define the reinforcements on the various structural elements, so let's see the different elements that the structural software has for the definition of the reinforcements. From the navigator, if we go to the Reinforcements node and select the reinforcements of the column, we find tables without reinforcement. But the software gives us the tools to customize the reinforcements, as in this case. We add 4 12mm rebars along the long side of the column and 16mm rebars in the vertices. We can also characterize the reinforcements of the stirrups. In this example, we assume a constant distance between the stirrups. We also have the possibility of adding stirrups in the junction. Once the reinforcements of a column have been drawn, using the duplicate function, it is possible to duplicate this reinforcements to the other columns. Let's now see how the reinforcement is modeled in a beam. Select a beam, right mouse click and select the reinforcement view. As for the column before, the table does not have any steel. At this point we have to manually design the reinforcement. The software offers us specific commands for the design. We activate the top bar command, we start designing the steel of the beam. Then we design the lower reinforcement and we characterize the bars. Then in the properties, we specify the number of bars and the diameter. Sometime, for existing buildings, a certain level of rebar bending was applied to contribute to the shear forces. Let's see how the software allows us to design these reinforcements according to such criteria, or according to the indications of the original documents of the building's reinforcements, to better represent the reinforcements. About the bending reinforcements or the stirrups, we can differentiate the pitch at the ends concerning the stirrups of the central area. For example, in this case, we put the stirrups with a pitch of 10 cm for the ends, while in the middle we put the stirrups at every 25 cm. Once the reinforcement has been added to a beam, through the copy function, we specify where we want to copy the same type of reinforcement, for example, in this beam. We can paste the modeled reinforcement. So these copy and paste functions are work accelerators, which allow us to speed up this phase with the manual insertion of the reinforcements. Once defined geometric model, materials, loads, level of knowledge and the reinforcements, we are now ready to proceed with the calculation of the model. In the calculation preferences, we need to specify the type of seismic analysis, selecting it from those offered by the software. Once selected, we must go to the Code Data node under the Seismic Analysis section and edit the parameters related to the reference site. When we calculate the elastic analysis with a structure factor, we must show particular attention to the factors that influence the structure. As for the verification of the most fragile mechanisms, the automatic program calculates, by setting a factor of 1.50 ELU per vertical earthquake, for the verification of vertical ELUs, always in the same working window. The structural engineer will have to specify in these fields. In the program he is indicating that we must specify in both directions the structure factor that we want to adopt for the checks. Once indicated, we can proceed with the calculation of the model.